Okay, very quickly. I'm going to go over halogenation. I'm going to go over aromatic, electrophilic aromatic substitutions. This is generally just taking an electrophile to an aromatic ring. So today I'm going to go over halogenation, nitration, and sulfonation. Try to go this super fast. So the idea is that the aromatic ring can go grab an electrophile, so it will function as a nucleophile. So we're going to look for electron charge density inside the ring to go out and grab something that's positively charged. So for halogenation, we think of halogens like Br, Cl, I then, and so generally they require different things for their reactions, but you can think of bromine and chlorine as pretty similar. You can use an iron catalyst to help this get going, and usually it's just the same halogen that you use attached to that iron. So very quickly, I'll just go over the reaction for this. So we have the ring, and then we're going to use, I'm just going to Cl. It's really all the same. And then we can use ferric chloride, or we can also alternatively use something like aluminum chloride. It truthfully doesn't make a really big difference. So we're going to look at is not this, but first we need to get this Cl to have a positive charge in order to have the aromatic ring really go grab that electrophile. So what we're going to do is we're going to touch the Cl to the metal. So we have this, and then we have Cl, and we have so what's going to happen is there's open orbitals on this iron so that this chlorine can attach to it. So when you get that, and what's going to happen is we're going to have something that looks like this after. These three chlorines are attached to the iron. I don't want to write it out to waste a little bit of my time, so I'm just putting it like this. So we're going to see there's going to be a formal charge right here. It's going to be positive. Obviously, it's really bad for chlorine. It doesn't really want to be positive. So what's going to happen is we're now going to have this benzene is going to do something like this now. So we're going to use one of the double bonds to grip one of the chlorines. So never forget formal charge. Formal charge. So what's going to happen is this is going to come here, and it's going to grab the chlorine, right? And then this is going to pop over here. So now we're going to have something that looks like, so you see we're going to break the aromaticity temporarily, and we're going to have a chlorine here, hydrogen, and because we lost this double bond, this will have a positive charge here now, and then we will still have Cl, FeCl3, this is a minus, and the chlorine can pop off to this iron. So we're gonna have a Cl minus. Now we essentially need a base so that we can eliminate the hydrogen and then regain aromaticity. So what's happening is we have this now, the chlorinated ring. And this chlorine will function as a base now. So it's gonna want a proton. So it's gonna grab this proton. Oh, that's not there yet. And this bond is going to go into the double bond to form a double bond. And what we're going to get now is chlorinated product, and then there will be HCl from the elimination, as well as the regenerated FeCl3. So that's just this reaction. What we're looking for in terms of selectivity is that we want there to be a pretty negative charge on this spot, or we don't want it to be positive because otherwise it won't really go seeking out this electrophile. Yeah, bromine uses, for bromine, we use this, and then for iodine, use this. And generally the mechanism follows really similar, so you can just rinse and repeat these really hard. Nitration. So nitration, the goal of nitration is that we're going to have a ring, we're at H9O3 in the presence of H2SO4, and we're going to add a nitrate, so NO2. Now, how does this happen? I'll do the mechanism very quickly. So we have our ring. Similarly, we need to really get this thing electrophilic. We need to make our nitrate group really electrophilic. So by doing that, we need to essentially change the form of it. If you notice, we have HNO3 at first, which looks like this. And we need to make, oh, this looks weird. Something looks funny. Here we go. We need to make it so that this is extremely electrophilic. So what we're gonna do is we attach H2SO4, a strong acid, and our goal of H2SO4 is to basically protonate this, and we're going to have a leaving group of water. So this is going to donate an H+, H+ right here, basically. Either H2SO4 is just H+ ion. And this oxygen has a lone pair here, too. So I'm going to grab this oxygen, and we're going to change this into now water is pretty stable, it'll leave, so we just go like this, and then we'll have that, but this is really unhappy right now. This is a 2+ because we just have 3 bonds attached to it, so this is going to turn into like a, yeah. So now we've got our electrophile, and now we're going, and this is a special electrophilic essentially because the oxygens are very electronegative, so those have a very, very positive character, so it's really going to want an electron. So with that, keep that in mind. I basically just created NO2 now, right? So we've got our NO2 ion now. Essentially this. It's gonna reach out, grab this nitrate. And what's going to happen is this is going to pop over. This is going to go here because we can't have 5 bonds on the nitrogen. So we're going to have this positive charge here now. We have a hydrogen here. So now we need another elimination. So we can just use the HSO4 that we generated earlier when we deprotonated our sulfuric acid. And we're going to, it's basically the idea is that we're going to make an electrophile. We're going to use the base that we generated from it to eliminate this hydrogen and restore aromaticity. And we're going to do that every single time. And this is going to give us there we go. So you notice this is a very strong withdrawing group because the oxygens are there through another effect, and this nitrogen has a positive charge. Nitrogen does not want to be positive. All right, nitrogen. Now for sulfonation. So sulfonation is the addition of SO3H. So our goal is to add SO3. Yeah, SO3. You'll probably see what's going to happen. We're going to protonate the sulfur. Sulfur looks like this at first. Sulfonate group. And we're going to have H2SO4 donate a proton. As you can probably guess. Here. Wait. I'm not sure which way the arrows go. Arrows go to this way. So I'm going to grab that. And we're going to have. So let's shift over here. We're going to get. Okay, cool. Now this is our electrophile. Sulfur has a positive charge on it now. So now we have the opportunity to use this electrophile. Basically the same mechanism all over again. So this is SO3H. Just keep in mind there's a positive charge on the sulfur. Just going to go grab the sulfur. Get rid of that. SO3H. Sulfur's happy now, but we lost aromaticity. You can probably guess what we're going to use for our base. The deprotonated sulfuric acid, and it has a negative charge now, so it's ready to go grab this hydrogen. So I grab the hydrogen, donate that bound in, and we will have sulfonated our benzene. So those three are all electron withdrawing groups, which means that we will be deactivating the ring because in these reactions, we're using the electron density within the benzene ring to go grab a positively charged electrophile, or an electrophile in general. So in terms of EAS, which is electrophilic aromatic substitution, we will have deactivation, which means that further reactions will be slower if we try to do further EASs.